Hey everybody, Mr. Bullock here. This stat lesson is on correlation. Let's go ahead and start the board problem here. So using the stem plot from the prior board problem 14, which of the following is the correct statement? The American League plot is reasonably symmetrical. Well, let's take a look at that. I think I have it over here. Yeah, that's pretty symmetrical. Okay, so A looks like it's true. The National League plot is slightly skewed to the left. Let's see. Yeah, slightly skewed to the left because of this little tail right here. So it's looking like more than one answer. The median of the American is higher than the Nationals. We determined that in the last board problem. It was. So the 29 in the National is not an outlier. Well, I'm getting all of these to be true, so I'm guessing this one's true also. So the answer is answer E. Okay, so correlation. Correlation is used with the letter R. So a scatter plot is strong if the points lie close to a line, whether it's going up to the right or down to the left, or down to the right. And is weak if the points are widely scattered about the line. Okay, so weak or strong, positive or negative. Here we go. All right, so here's one right here. What would you say? Is that weak or strong? Or positive or negative? Okay, what I'm going to do is, what about these two guys? Which one's stronger? Well, if you look close enough, you guys, one is the axis. They're the same graph. I just changed the scale. This is the same points right here, except the scale on the x-axis and the y-axis are different scales. So here it's zoomed in, here it's zoomed out. So if you zoom in, it's the same scale. So which is stronger? It's the same graph, you guys. So I would say that that is a moderately weak positive association. Okay. So another measurement is called correlation. It's used to measure the strength of your plotted points. Okay, so the correlation R measures the direction and the strength. If it's positive, then it's going up. If it's negative, it's going down. And measures the strength of a linear relationship between two quantities. Okay, so given a set of ordered pairs xy, the correlation is this, you guys. There it is right there. So your correlation is m sub xy minus mx times m sub y over s sub x times s sub y. Okay, now this s sub x and x sub y is actually your standard deviation. So I'm going to go ahead and put in my standard deviation formulas here shortly, you guys. So this just means standard deviation. Okay, so the sigma. Okay, where m of x is your mean of your x's, m of y is the mean of the y's, s sub y is your standard deviation of the x's, and this is the standard deviation of the y's. And then this is, if I multiplied x times y's and averaged those out, this would be the mean of the products of x and y's. All right, and yes, our calculator does most of that, and let's try this, you guys. So here are the lengths of the two bones in five fossil specimens of the extinct Archaeopteryx. I think that's how you pronounce it, Archaeopteryx. Okay, so here they are. You got your femur and humerus. All right, and this is found on page 138, exercise 319. So what we're going to do is put the femurs in list 1 and the humerus in list 2. Okay, so go ahead and do that in your calculators. Clear your lists out first. Okay, and put your femurs in list 1 and your humerus in list 2. And then we're going to do a two variable stat. So you're going to hit, after you do that, hit your stat button, scroll over to calculate, and then do a two variable statistics. And when you do a two variable statistics, you're going to get, it's going to be a two, so you're going to see this, two variable stats, and you plug in list 1, comma, list 2, comma, and then hit enter. Okay, and when you do that, it's going to give you this blue information right here. Okay, and then just note that this means the standard deviation of x, which is that right there, and this is the standard deviation of y. So sometimes your book uses this symbol, sometimes your book uses this symbol. I don't know why they go back and forth like that, but your calculator uses this, s sub x, or which is your standard deviation of x. Okay, and what this is this is the sum of the products of x and y. So I don't know why they just, it's just a real simple added program. To divide it by the number of numbers, they would just divide it by 5. But what you're going to do is take this and divide it by 5 to find the average of them, because this is what they add up to. You just need to do one more step. You need to do that manually and take this number and divide by how many pairs there were. There were 5 pairs. Okay, so divided by 5, and then, so now I have everything, you guys. I have everything for my formula that I'm going to go ahead and plug in to right here. Okay, I know this now. We just did that. I know my mean of my x's and my mean of my y's. Let's go back. Okay, let's see. So, and that's all in your calculator right there when you plug all that in. And here's my mean of my x's is right here, my x bar. Okay, here's my mean of my y's. And then here's my standard deviation of x's. Here's my standard deviations for y's. Here's my m of xy, my mean of my products of x and y. So plug all those in, and you get that. Okay, and so when I plug all of that in, I get about 0.795. All right, so what's that mean, you guys? What does that mean? So the properties of correlation are this, you guys. Both variables have to be quantitative. You cannot have a categorical variable. Okay, so they both have to be numeric answers. Okay, and if and your correlation R is in between, inclusively between -1 and +1. And if it's close to 0, then it's a very weak linear relationship. The scatter plot is scattered all over. Okay, if it's close to -1, it's a strong linear relationship. If it's close to +1, it's also a strong linear relationship. Okay, so when R is positive, it's a positive association, and when it's negative, it's a negative association. R describes linear relationships only. R is not resistant to outliers. I'll show you some examples in the next lesson. And when describing relationships between two variables, always include your correlation, always include the mean of your x's, which is your x bar, this is your y bar, and always include your standard deviation of your x's and your standard deviation of your y's. Alrighty, so figure 3.9 shows the correlation of scatter plots describing strength. Okay, so here when they're scattered like this, your correlation is virtually 0. Okay, this is virtually 0 also, but this is kind of, I guess it's going down to the right, so it would be a negative. It's -0.3. Okay, this is going up, but it's still not a real strong linear relationship. This one's stronger, so the closer they are to +1 or -1, the more linear they are. So this is closer. These points are more linear than these points right here. R is 0.5. Here R is -0.7. Here R is 0.9. Here R is -0.99. So the closer they are to -1 or +1, they become very linear. Okay, so that's what correlation does. So the patterns that are close to a straight line have a correlation closer to -1 or +1. Okay, so adding or subtracting does not change your correlation. So for example, we're going to look at this example on page 145. All right, so competitive divers are scored on their form by a panel of judges who use a scale from 1 to 10. The subjective nature of their scoring often results in controversy. So we have the scores awarded by two judges, Ivan and George, okay, on a large number of dives. How well do they agree? Well, some of the we're going to do some calculations, or there is some calculations done, and we find that the correlation between their scores is 0.9. That's pretty strong. But the mean of Ivan's scores is 3 points lower than George's mean. And they don't contradict each other, they're just simply different kinds of information. The mean scores of Ivan's awards much lower scores than George, but they're consistent, you guys. That's the big thing. Because Ivan gives every dive a score of about 3 points lower than George. The correlation remains high. As long as they're the same all the time, the correlation remains high. They correlate very high. If I knew George's score, I'd just subtract 3, and that'd give me a good approximation of Ivan's score. So adding or subtracting the same number to all values of either the x or y doesn't change your correlation. It keeps it the same. If Ivan and George both rate several divers, the contest is fairly scored because Ivan and George agree on which divers are better than the others. So the high correlation shows, the high R shows their agreement. But if Ivan's score on one diver and George on another, we must add 3 points to Ivan's score to arrive at a fair comparison. Okay? All right, so you guys go ahead and try some. If you're in my stat class, I would assign that for your homework. Take care.